we have sort of seen that the modern solutions prefer that magnetosphere is largely force-free, and there is a current sheet which is equatorial, and then it splits into separatrix and then arrives at the pole around the last closed field lines. And those areas are the primary active areas where accelerating potentials exist, and you can have generation of pairs and acceleration of particles, and those are the regions which are the likely active regions for radiation. And once you include frame dragging effect due to general relativity, then you can also see that in some part of the polar cap is also available for you to accelerate particles, because electric field cannot be fully compensated by space-time. So as a result, you now have a distribution of regions where particle energies can reach high enough values for you to generate the kind of radiation that we see from pulsars. And this is one of these calculations in Philipov 2015, where you can see the distribution of electrons and positrons under the assumptions that have gone into this paper on this particular calculation and where they are. And we have also seen this in the previous lectures. If you now have an oblique rotator, then you have this equatorial current sheet that opens up like a ballerina skirt, and you get this larger open regions where you can have the particle acceleration and flow, and including now the polar cap region where because of GR you have particle accumulation. So this is electron density, positron density, ion density. And this is a diagram of photon density in this particular calculation, where they have gone from the particle density to photon density, assuming a certain emission mechanism and a certain conversion from the type of particles and to the type of radiation we see. And this primarily relates to high energy radiation. So now there are certain caveats that one has to keep in mind. The magnetospheric solutions give you regions where E dot B is not zero. It gives you regions where E dot B is primarily zero. However, it does not tell you from first principles that in regions of E dot B not equal to zero, what will be the number of charged particles present. It gives you a value for the total net charge. However, since we're talking about pairs, that net charge is met by a large multiplicity of pairs where the difference between the two numbers of electrons and positrons provides you the net charge. But it doesn't tell you from first principles as to how many generations of pairs will be there, what will be the pair multiplicity, so that you can have a full idea of what is the energy per particle in the pair, and particularly in the case of coherence and so on, what is going to be the amplification factor. But the radiation mechanism crucially depends on the actual number of particles and the energy per particle. So this gap is not yet closed in this kind of simulations. So going from the electric field distribution to the radiation is still, it still involves a number of assumptions which may or may not be right. Okay. So
so what this kind of models, this multiplicity is kind of parameter which
multiplicity is assumed. A certain multiplicity is assumed, and it is assumed for computational convenience. So for example, some calculations will assume multiplicity is 100. In reality, it may be millions or even billions, right? But that is not easily tractable when you try to do a numerical simulation. So they limit the multiplicity to something that can be handled in the computations. But there is no a priori limit to it, which comes from these calculations. So these results are also generated that way, having assumed a certain maximum multiplicity, and then you just try to fit it. Also, radiation mechanisms can be of various kinds. Today, we will just review certain sets of radiation mechanisms which could be relevant for emission in the pulsar magnetosphere. Calculations like these, they do not explore all manner of radiation mechanisms. They just assume a certain radiation mechanism, converting the particle energy density to radiation energy density. And primarily, most of these calculations just use curvature radiation as the primary source of radiation, which may or may not be true, particularly for high energy radiation and particularly at large distances from the stellar surface. So, radiation-wise, there is still a leap that needs to be taken from the magnetospheric models that these new calculations are providing to modeling what we actually see in pulsars. Okay, so today, as I said, that we will start talking about radiation. I am not going to do anything specific to pulsar magnetosphere today for radiation, but today's job will be to just review the different mechanisms that we may think of applying in pulsar magnetosphere. So, certain concepts, let us recall and just make sure that we are fully fully familiar with it, because as we try to explain radiation, all of these concepts will be important. So, radiation that we are going to talk about are radiation from accelerated charges. And these accelerated charges, given a acceleration a0, this is proper acceleration, that is acceleration in the instantaneous rest frame of the charge. Okay, the charge may be moving with some acceleration. At any given point of time, it has both velocity and acceleration. But we go to an instantaneous rest frame so that the instantaneous velocity is 0, and then measure the acceleration in that frame, and that acceleration is a0, and in that case, the power emitted in that frame can be written as 2 by 3 c cube q square a0 square. This is in CGS, but q is the charge. Now you can see that this is square of the charge, so therefore the sign of the charge doesn't matter. So electron and positron will radiate exactly the same amount. Also, notice that this is in the instantaneous rest frame of the particle. So the person who is observing this, who is in the observer frame, with respect to whom the charge may be in motion, the actual radiation received will be different. So you have to do a Lorentz transformation between that frame to the observer frame to get the power as received. Now, if you want to use observed values of acceleration, let's say in the observer frame, the particle has an acceleration and the particle has a velocity. Now I can decompose that acceleration into acceleration parallel to velocity and acceleration perpendicular to velocity, right? Now once you do that, then from those measured quantities, acceleration parallel to velocity and acceleration perpendicular to velocity, I can construct this quantity a0 by this Lorentz transformation equation. So measured acceleration perpendicular velocity is this, and parallel velocity is this, and gamma is 1 by 1 minus square root of v squared by c squared. So this is the Lorentz factor. So using the Lorentz factor, I can construct this A0. So then I can compute the power radiated in the rest frame of the particle, and then I have to Lorentz transform that power to get the observed power. Okay. So
this A0 is like what from the observer frame.
No.
Sorry, A0 is in your particle's rest frame.
That is correct.
And A perpendicular,
This is an observer frame.
This is an observer frame. So in the observer frame, if it has some acceleration A, we decompose into two parts.
Yes.
And then we can put it back there in that equation, and then we can say that from observer we'll see the power in some perpendicular direction to the motion. We can.
No, so this is the power.
Yes. So
in the rest frame. Yes. Now that power you have to Lorentz transform again back to observer frame to get the actual power received. And then you will pick up directionality. Okay.
Now if we substitute this A0 square over here to that equation,
then you will get the power radiated in the
charge.
Rest frame.
Yeah.
Charges rest frame.
And then take it back.
Yeah. So I have sort of shown that pictorially here. I have not given you any expressions. So suppose it's a stationary dipole, and you have for each emission mechanism there will be emission pattern. Usually it is not. No emission mechanism gives you absolutely isotropic radiation. So depending on the emission mechanism, you will have a pattern. Now, simplest emission mechanism you can think of is an oscillating dipole. And if there is an oscillating dipole with axis as indicated over here, then you get this cos square theta pattern or sin square theta pattern in your emission. Now this sin square theta pattern, if you now have a velocity, so let's say the observer is moving with respect to this dipole. So in the observer's frame, the dipole has a certain velocity. Then once you transform this to the observer frame, you will have a distortion. And this distortion needs to be taken into account when you look at the actual received power, and that will depend on the direction of the observer, that will depend on the direction of the velocity, and that will depend on the direction of the acceleration. And this is the result of aberration of directions between the two frames. And when you look at the actual power, you have to take into account the Doppler shift. So basically each time interval gets transformed into another time interval. So therefore in the rest frame, energy emitted over a certain time interval is now received over a different time interval. So that transformation has to be made. The energy sent, radiated at a certain frequency is received at a different frequency. So that correction has to be made as well. So once you do all that, you get the power received at the observer. Next, another important thing that we will worry about while talking about pulsar radiation is polarization. When you're talking about radiation from an accelerated charge, if you take a single charge and take one instant, radiation is entirely 100% polarized and linearly polarized. Because the electric vector has a defined direction, which is proportional to this vector quantity, where n is the line of sight, unit vector along the line of sight. Beta is the velocity of the charge divided by c. Beta dot is the acceleration of the charge divided by c. And n minus beta crossed with beta dot, and that cross product is crossed again with n, gives you a fixed, a specified direction, which gives you the direction of the radiation electric field. Now, if all these quantities are non-varying, at least non-varying in direction, then you will have a 100% polarized emission from this charge as you integrate over time. But in general, that is not true. In general, two averages will happen. For a given charge, as time progresses, it will go to regions where the direction of acceleration can change and direction of velocity can change. Because acceleration is going to change velocity, unless the velocity and acceleration are absolutely parallel to start with, the velocity itself will change direction. So, over time, you will get an averaging of directions of electric vector that a single charge will produce. But there is no situation where from a cosmic source you are looking at a emission from a single charge. You are always aggregating emission from a large number of charged particles. And this large number of charged particles will be distributed over a region, and they will have their own independent velocities and independent accelerations. So therefore, even though this entire volume may be small and the n is by and large the same for from all positions of these charges, because of the difference in beta and beta dot, you will have, even at a given instant, averaging over a large number of charged particles. So that will also bring down the degree of polarization. You will get an electric vector which is a combination of all of these things. Now, I will come to this later when we talk about coherent radiation. So coherent radiation is a special situation where you have multiple charged particles sharing quote unquote a given location. Now the given location is, of course, in a true sense it cannot be correct, but we look at location in units of wavelength of the radiation that is being emitted. So anything which is much smaller than the wavelength of the given radiation, the different locations within that region, we can treat them as a single location. So if there is a large number of charges which share a location which is much smaller in size than the wavelength of the radiation being emitted, then we can consider them to be a single combined charge. Not only that, they have to share the same velocity and same acceleration. So now, in same location, same velocity, same acceleration, then what can happen is that instead of adding power from individual charges, we can add the electric fields from the individual charges in coherence, which means basically the charge Q here can then become NQ, where N is a number of
transforming this to a moving frame, this is in the rest frame of the particle, right? So how do you transform this to observer frame, the spectrum?
The spectrum, the same way you transform power. This is the same, this is also power. So this standard Lorentz transformation will apply. You have to transform the time, you have to transform the frequency, you have to, and you have to transform the direction. So aberration, Doppler shift, and time. We need to take it. So this is what I was mentioning, that if you have n charges, if the radiation adds incoherently, then you can think of each particle providing power p, and with n particles you get n times p. Whereas in coherent emission, q goes to nq and p goes to n square p, and this requires branching in a scale much smaller than the wavelength of the emission that you are talking about. So obviously this is helped if the wavelength is large. So in pulsars we will encounter coherent emission when you go to long wavelengths, which is radio frequencies. Whereas in high energy emission, like optical or X-rays or gamma rays, this is not a viable situation, and we don't see. Okay. So now we are talking about these members of these pairs, that is electrons and positrons, being released in a region where there is an extremely strong magnetic field. So what is the general motion of electrons in such a situation? So if you have an electron which is released perpendicular to a magnetic field, then we know that it will undergo a circular motion, and it will produce what is called a cyclotron radiation. And the cyclotron radiation in the extreme non-relativistic limit has a given standard frequency, and that is a function only of the magnetic field and the mass of the particle. And the mass of the particle in the extreme non-relativistic limit is the rest mass. So you have in CGS units, you write it as the electron charge times the magnetic field divided by mass of the electron times speed of light. Right? So EB over MC is your cyclotron frequency, and that cyclotron frequency is the only emission that you will get from this particle. It's a particle in a moving circular orbit. But once you take into account that the electron could be not extremely non-relativistic, but it has a finite speed, and that finite speed will require some relativistic corrections to this, special relativistic corrections. And that then distorts the spectrum, produces harmonics of it. And here is an example of the kind of emission that you will see for an electron moving at 0.4 times the speed of light. So this is the fundamental. But then you have all these other harmonics also that appear. And when you add it all up, then the total emission. So you can go from basically a resonant emission. This is a resonant emission to a continuum purely because of relativistic transformations from the instantaneous rest of the particle to the observer. And we can take a look at it in a little more detail. So you have, let's talk about synchrotron radiation now, which is the ultra-relativistic limit, where Lorentz factor is close to 1. And you have electron gyrating around the magnetic field. It can have a motion along the magnetic field which is not affected by the magnetic field. Velocity parallel to the magnetic field is not subjected to an acceleration due to the presence of such an electron. If you look at it in the orbital plane, it goes around, and because of the aberration and beaming, the radiation pattern has now become squeezed to within about 1 over gamma in the forward direction. And when this beam passes across the observer, you get spikes in the electric field like this. When it goes away, you don't see this big lobe. You see some tiny thing which is negative at the back, so it goes there. And then when it passes again, you have this periodically pointing at you. Fair enough. What is the spacing between these periodic pulses? What do you think is the spacing between these periodic pulses?
The time taken for it.
That is the gyration frequency, inverse of the gyration frequency. And what is the gyration frequency?
That is proportional to magnetic field.
Okay, so gyration frequency in the cyclotron case was EB over MEC. So what will it be in this case? EB over gamma MEC, because mass is now replaced by the effective mass. So gamma MEC. So now this gamma which you are talking about, this comes from a velocity as seen by an observer. Which observer?
Observer moving along the magnetic field.
The observer at rest with respect to the magnetic field.
With respect to magnetic field.
With respect to the magnetic field. Okay? So when we say that the gyration frequency is EB over gamma MEC, now if you take a car and drive at high speed, this is not going to change. If you take a car and drive at high speed, that is not going to change. EB over gamma MEC, that number will still be the same, because that gamma is referred to the observer who is not you, but the observer at rest with respect to the magnetic field. Okay? So, so that is the rate at which it will repeat. And because this profile is not sinusoidal anymore, if you Fourier analyze this, you will get not just the fundamental frequency but many higher harmonics. And that is an overlap of those harmonics is what you saw, is when you add them up, you get a continuum. And that continuum has a shape like this, where the peak comes at gamma cubed times the gyration frequency times sine of what is called the pitch angle. The pitch angle is the angle between the velocity vector, instantaneous velocity vector, and the magnetic field. So now remember, this omega h is EB over MEC divided by gamma. So therefore, this peak frequency is actually proportional to square of the Lorentz factor and not cube of the Lorentz factor in this case. This omega h is EB over gamma MC. So therefore, this peak synchrotron frequency, characteristic synchrotron frequency, is proportional to gamma square, not gamma cubed.
Yeah.
Okay. So if you write it numerically, then it is about 0.81 times gamma squared megahertz for 1 Gauss of magnetic field and electron. So an electron in a 1 Gauss magnetic field has a synchrotron peak frequency of 0.8 gamma square megahertz. An electron in 1 Gauss magnetic field, if it is non-relativistic, what is the frequency that it has in numerical terms? Here it is 0.8 gamma square megahertz. If gamma tends to 1, very close to 1, then it is not 0.8 megahertz. It is 3 megahertz. And that happens because of this 0.29 factor. Okay, so when you have in the ultra-relativistic case, when you superimpose multiple harmonics, you get this shape. Here we are not talking about the frequency of individual harmonics. We are talking about the shape of the envelope. The shape of the envelope peaks at a value which is not omega c by 2 pi, but 0.29 omega c by 2 pi. Okay, so that's the reason why the peak gets reduced somewhat. So in non-relativistic case, it is 3 megahertz per Gauss. In synchrotron case, it is 0.8 gamma squared megahertz per Gauss. But this is to be applied only when gamma is much larger than 1. Okay. Okay. So now, what is the power emitted per particle? And that is again proportional to square of the Lorentz factor, proportional to velocity square, but we know that this is ultra-relativistic case, so beta square is roughly 1. So we don't need to worry about that. Thompson cross-section times speed of light. Okay. This is the energy density in the magnetic field, which is b squared by 8 pi, right? So this is proportional to square of the magnetic field. So the frequency is proportional to the magnetic field, linear order. Power is proportional to the magnetic field, square. Both are proportional to Lorentz factor square. And this is, again, depends on the charge. So for an electron, this factor is 1. So if you put in the numbers, then it is 2 times 10 minus 14 gamma squared ergs per second per particle for 1 Gauss magnetic field. So you keep these numbers in mind because we will compare these with various other elementary quantities. So this is the summary. For Lorentz factor of the order of 1, you have cyclotron frequency, which is 3 d Gauss megahertz. And if you look at the corresponding h nu or photon energy, it is 12 b12 keV. Okay, so these are rough rules of thumb. It's 11.6. So remember, it is 12 b12 keV for 10 to the 12 Gauss magnetic field. The photon energy that is emitted by cyclotron emission is 12 kiloelectron volts. When you go to ultra-relativistic case, the synchrotron peak frequency is 0.8 gamma squared d Gauss megahertz. And similarly, if I write the energy of the photons, then it is 3 gamma squared b12 keV. This 12 has come down to 3, and you multiply it by gamma squared. So it's the same factor. And the gyration frequency is the gyration frequency in non-relativistic case divided by gamma. Getting slightly cut off at the right edge. Then synchrotron power per particle is, as I said, 2 times 10 minus 14 gamma squared bg squared ergs per second. We can write it in different units. When I put pulsar-like magnetic field 10 to the 12 Gauss, then you can see the enormity of this quantity. It is 1.25 times 10 to the power of 16 MeV times gamma squared for 10 to the 12 Gauss magnetic field per second. Okay. So once you put a particle in this magnetic field and it starts doing its radiation, in some time it would have spent all its energy doing this radiation. And once it spends all its energy doing its radiation, it can get stuck at the lowest Landau level around the magnetic field. The lowest Landau level has a perpendicular momentum with respect to the magnetic field that is 0. Okay, the lowest Landau level has 0 perpendicular momentum across the magnetic field. Parallel momentum is not affected by this radiation. So coming from an arbitrary energy, starting from an arbitrary energy to come down to the lowest Landau level, the time that a particle can survive before coming down to the lowest Landau level is called the synchrotron lifetime. The synchrotron lifetime you can compute by taking the initial energy and dividing by the emission rate, and that turns out to be for 10 to the 12 Gauss magnetic field, 4 times 10 minus 17 gamma to the minus 1 B12 to the minus 2 seconds.
Is the initial energy of the population of the particles that we are starting with?
Any particle that you put in with a certain value of Lorentz factor. So the energy of the particle is encoded in the Lorentz factor.
So typically if we want to calculate, say for example, the charged particles which are getting emitted, say from, they have been taken out by the magnetic field from the surface of the star,
Right.
we can compute the energy from the acceleration potential.
That is correct. So you have to,
And that energy we put it into this d
Yes.
dt by e with e by d dt we do, and we get that time scale in which it will come down, and then this motion along this thing will start.
right. So the time to radiate away the perpendicular energy in the perpendicular momentum is what is the synchrotron radiation lifetime, right? And you have to supply an initial energy to this particle,
Yes.
right? And that initial energy is what is talked about here. So this gamma, as we put it here, is corresponds to the perpendicular momentum. Yeah? So
So it's almost instantaneous in case of pulsar.
almost instantaneous in case of pulsars close to the surface.
Close to the sun.
Okay. If you have 1 Gauss magnetic field, then it is 1.27 years.
So that means suppose if there has been sudden some production of charges near the light cylinder, over there the magnetic field is quite low, and over there all the emission what is going to happen if via this synchrotron emission, because there is also those populations. So it is those particles will take comparatively longer time. So emission is not going to come from curvature radiation, one can.
This is not curvature, this is synchrotron.
No, this is synchrotron, but what will happen that once they come down,
Yeah.
and then they start getting dragged along the magnetic field due to this parallel component, then dominantly after this cyclotron time, the emission what we can say that it will be kind of curvature emission, right?
No, not necessarily. Because the motion is along curved field lines, right?
Yes.
So as you move along curved field lines, then at some point the linear momentum, as soon as the energy of the particle becomes sufficient so that it can excite higher Landau level excitations, because the Landau level separation is coming down as you move along the magnetic field.
Yes.
So at some point it is possible to excite the next Landau level
Yeah.
and the next Landau level.
Yes.
So then perpendicular momentum will build up, and you start getting synchrotron radiation again.
Yeah, so before going to that regime, suppose it from the stellar surface, as soon as it goes to this zeroth level, then for some time it will keep on moving
Yeah,
in
so
that state. So there
only
is
curvature radiation is possible.
only
in that
curvature
state.
radiation. Then after some time scale, it goes to synchrotron,
Yeah,
and it goes on in that way after that.
that is correct. That's what is going to happen. And remember that Lorentz factors that you're talking about could be very high, right? So here, 1.27 years, but you come to the wind zone and so on, where magnetic field is still not 1 Gauss, but much larger than that, and Lorentz factors could be millions. So even for 1 Gauss magnetic field, if you have Lorentz factor of millions, then your synchrotron time scale is seconds. Okay, tens of seconds. So it is still quite small if you have large Lorentz factors.
So that means primarily if we are looking at the emission from those regions, it will be primarily synchrotron emission what we will see. Can we
No,
see?
that you will have to compare with what other mechanisms are present. I mean,
That's true.
okay. Now, let's compare these numbers also with some other relevant quantities. And that is, once you have a high energy photon which you create, so because T is equal to n small, that means all the energy is dumped very quickly into photons. So these photons will have to propagate in the same region of the magnetic field. And as we have already discussed, this is prone to creating pairs. So how far will the photon will the photon have to propagate to be able to generate pairs? And that is this pair is the mean free path of the photon before pair production. And if you put in the numbers, then this is 2.3 angstroms is the distance it has to move. If the perpendicular component of the field perpendicular to the direction of motion of the photon is equal to the quantum field, which is 4.4 times 10 to the 13 was, and e to the power of 4 by 3 chi, where chi is roughly 1 for magnetic field equal to the quantum field, and energy of the photon being 1 MeV. You need a minimum of 1 MeV for pair production. The photons can have much larger energy as well. And the larger the energy, the smaller is the value of this. So this, as chi increases, this exponential factor will tend to unity. It becomes closer and closer to 1. And so you have really a very small distance to go before you can produce pairs and pair cascade can happen. But remember, this quantity is not the local magnetic field itself. It is the component of the magnetic field which is perpendicular to the propagation of the photon. Most of these photons that are emitted, they're emitted from particles moving along the magnetic field at very high Lorentz factor. So all the photons are emitted in the forward direction, and it is emitted tangent to the local magnetic field. So the photons has to travel much larger distance than this to pick up a perpendicular component which is significant. So this 2.3 angstrom is not the relevant length scale for the photon propagation, but you will have to move enough distance so that this bq by b perpendicular has a significant value. Otherwise, this is very large. Because it is extremely large, so it could exit the magnetosphere without producing any pairs, unless b perpendicular builds up. So that's what decides. So that is larger. B perpendicular will be quickly larger if the magnetic field is more curved. And this has been a debate in pulsar literature. So if you take pure dipole magnetic field and take the curvature that is provided by the dipole magnetic field, can the photons that you generate produce enough pairs within the gap between the other polar gap? It looks very difficult. So most people sort of resort to saying that near the surface there are other multipoles which contribute to a larger curvature of the magnetic field, so that you can get sufficient B perpendicular quickly enough to produce pairs. So this you should remember, that injecting pairs is not necessarily just a question of energetics. It has also relation to the geometry, and this geometry is favorable when you have larger multipoles contributing near the surface. And this has been recognized right from the beginning, including Rudolph and Sutherland paper. So where they take the radius of curvature of the field line to be much smaller than the radius of the star. And that is only possible if you have larger multiples and not just double.
I have one question, is that I don't understand the physical significance of this quantum critical magnetic field. What it actually, suppose how I can compute it, is at what limit?
Oh, this is just, yeah, so it is where the energy of the Landau level becomes equal to the rest energy of the electron.
Energy of the
Landau level is similar to the energy of, rest energy of the electron.
Which
Landau level.
Which it is quantized. So zero.
No, so Landau level spacing basically. Yeah.
Oh, Landau level spacing.
Yeah. So
but it will it's changed with magnetic field.
that is the magnetic. So the magnetic field at which the energy of the first Landau level becomes comparable to the energy of rest energy of the electron.
Okay. So what is physically what it means if that kind of scenario happens, that the magnetic field is strong and such that the rest mass energy is equivalent, is equal to this energy. So what can happen if you get this kind of system? What will happen physically? What will happen?
No, nothing much changes. This is an unit.
Yes.
This is an unit that is used in the quantization calculation for synchrotron radiation. So,
what
there is no physical change that is happening just because you are going above that field or below that field. So, if you go much higher, then there are things like vacuum polarization and so on can happen, where you can have spontaneous generation of pairs from vacuum. So that requires this energy, the field to be larger than this this limit.
Because magnetars come with more magnetic field.
Yeah,
than this, right?
that's correct. So that's why vacuum polarization is something that is relevant in the magnetar atmospheres. So when you do radiative transfer, you have to take into account vacuum polarization. But so that necessarily requires that the field has to be larger than this limit. But for synchrotron radiation itself, there is no change in physics as you change the magnetic field above this limit.